Today I will start a new part of crystallography which is very important. I will introduce you to reciprocal lattice because this is the most important part that one should understand in the theory of diffraction. What is reciprocal lattice and how is it important? See, we have gone through Bragg's law, right? What is Bragg's law? N lambda equal to 2t sin theta. So, the relationship is sort of inverse when you try to write what is the value of sin theta, which is n lambda by 2d HKL, which actually means the relationship is inverse. With respect to theta. And larger the d value, smaller is the value of sin theta. And it is also difficult to understand when the lattice is considered and you try to draw the planes inside the unit cell with different d values. What happens is, in the lattice, suppose if this is my unit cell, some planes which are parallel to the faces are easy to see. Some planes which are like that are not so difficult to see. But then when the planes are intersecting all the three axes in all possible directions, it becomes difficult to imagine. And then what are we saying in Bragg's law is the constructive interference of X-rays upon diffraction occurs when the phase difference, path difference is integral multiple of wavelength. So now what we are trying to see is we are trying to see that diffraction occurs from a set of parallel planes. What we want to do, we want to measure all the reflections from all different planes. So what we need is all the crystallographic planes that one can consider inside the unit cell has to be placed in front of the beam in such a way that it meets diffraction condition. Otherwise, you will not get a full data set. Because as I said, a full sphere data corresponds to HKL values ranging from plus minus infinity to plus minus infinity. This gives you the complete data set. And when you have, suppose, A, B, C values like 10, 15, 20, then H is about plus minus 11, K is about plus minus 16, and L is about plus minus 21, gives a full sphere data up to 50 degree to theta. That is the IUCR requirement for a full data set for a routine structure solution. So if you want to collect data up to 2 theta equal to 50 degree on such an unit cell, this set will represent a full sphere data. So you can imagine how many large number of combinations are possible and how many reflections are to be collected. That means you have to orient the crystal in that many ways. Then only the beam will meet the diffraction condition, because here the beam is fixed. You have to only rotate the crystal in different directions. So to understand or to make a procedure or a strategy for data collection, it is not very easy if we just consider the planes. So instead, what is considered is points. Every plane in the direct lattice is converted to a point by a particular method. And then we will see that those points, which are imaginary points originated from the real planes in the lattice, will correspond to another lattice, will form a new lattice. And then it will be easier for anybody to understand how, when you place a crystal, those lattice points or reciprocal lattice points are around the crystal. So what we try to do is to suppose I have a two-dimensional lattice. I have drawn two unit cells, and this is my origin 0, 0, 0. So now, what I am trying to do is, I have one set of parallel planes going like that. So the perpendicular distance between them is what? See, these planes, suppose if I say that this is direction x, this is direction y, and z is towards u, this plane, which is like this, is parallel to x-axis and parallel to z-axis. So the corresponding mirror index for this plane will be parallel to x means 0, y 0. So this distance is d 0, y 0. What is y? It is touching y at one unit. So this distance is 0, 1, 0. Now, a set of parallel planes which are 0, 1, 0 set of planes, I am extending this line or cutting this line at a point start which is at a distance 1 by d 0, 1, 0. So this particular star marked point represents this set of parallel planes in the lattice. So this is the reciprocal lattice point corresponding to D10, D010, corresponding to 010 plane. So for this plane, this is the point. It can be outside, it can be inside, depending on what is the value of D. If the D, suppose if D010 is 5 angstrom, so this is 5. So 1 by D010 is 1 by 5. So it should be somewhere there, like that. Now, if I have a plane like this, what is this plane? It is parallel to Z. 110. So this is 110. So if I drop a perpendicular from here to there, is my D110. But then I am stopping that at a point here, at a distance 1 by D110. So 010 plane makes a reciprocal lattice point here. 110 plane makes a reciprocal lattice point there. What about this? This plane? This cuts x at half, y at 1, parallel to z. So it is 210. No, 120. Right. 120. Because x-intercept is half, y-intercept is 1 and 0. Sorry, this is not 120, this is 210. So 210. 210. Huh? 210. Intercept is half, 1, 0. Take reciprocal, it becomes 210. So now from here, if I drop a perpendicular, this distance is d210. I cut it at a point where the distance is 1 by d210. So now you see each and every plane in the unit cell is getting converted to a point. Where is the point located? At 1 by dhk distance. So if I draw if I suppose draw a cube and then suppose from this origin to this distance, suppose this is x, this is y, that is z. What is this distance? From origin to that is a, which is equal to this particular plane is what? 0, 1, 0 plane. So a equal to b 0, 1, 0, which is equal to d 1, 0, 0 is equal to d 0, 0, 1 for cubic system. So now for this edge length, suppose it is 10 angstrom cubic, where should I cut this point? 1 by d. So I cut it at some point here. 1 by d is 1 by 10. Where do I cut this one? Is again at 1 by 10. This one 1 by 10. So what I form is a small cube like that, which is my reciprocal unit cell. So the reciprocal unit cell length A star is nothing but 1 by A. B star is equal to 1 by B. C star is equal to 1 by C. These A star, B star, C star are the reciprocal edge lengths. In case of cube to orthorhombic, excluding hexagonal in between, cubic, tetragonal and orthorhombic, when the axes are at 90 degree apart, right, the angles are 90 degree, this relationship is valid. So this real unit cell gets converted to a unit cell or reciprocal lattice. So this relationship of A star, B star, C star is valid for cubic, orthorhombic and tetrahedron when the angles are 90 degrees. What happens in case of monoclinic? If this angle is beta, what are these two sides? A and C. Your B is here. And B is both perpendicular to A and C. Right? So now, taking this as origin, following the same rule, what is the distance between these two? What is the distance, this perpendicular distance between these two? This plane is parallel to B and C, that is 1, 0, 0. So this is, suppose if I write this as O, B, this, what is the distance between this and that plane? This plane, which is cutting C at 1 but parallel to A and B. 0, 0, 1. Right? What is this angle inside? Correct. How?
OAB and that angle is also beta, opposite to this.
Which angle? This angle is also beta.
And angle OA.
I was coming like that. If this is beta, that is beta, so this is also beta. Same thing. So this is beta. And these two are 90s. So internal angle should be 180 minus beta. So now my reciprocal lattice of monoclinic would correspond to A star, which is equal to 1 by B100, like that, and C star would be 1 by B001, because it is like that. A star is equal to 1 by A, right? A star is equal to 1 by A, that is 1 by D100 or D010 or 001, that is because it is cube. So now here, A star is 1 by D100. Now you tell me what is D100 in terms of A and beta. This length is what? A. This length is C. If this angle is beta, what is this angle? If this is beta, this is 180 minus beta. So this is also 180 minus beta. So now can I write what is OB? Considering this triangle. What is it? A sine 180 minus beta is equal to A sine beta. Similarly, if I take this point as Q, can I write what is OA? OA is C sine 180 minus beta is equal to C sine beta. So A star is 1 by D100, that is OB, that is equal to 1 by A sine beta, and this equal to 1 by OA, which is 1 by C sine beta. And this angle is the reciprocal lattice angle between the two reciprocal lattice axes. So that angle should be termed as beta star. So that beta star is equal to 180 minus beta. Here, since alpha equal to beta equal to gamma equal to 90 degree, alpha star equal to beta star equal to gamma star, once again equal to 90 degree. Here in this case we did not have to change the angle because they are mutually perpendicular. Here the angles are not mutually perpendicular. So now in monoclinic system, A star is 1 by A sine beta, not only 1 by A. C star is 1 by C sine beta, not just 1 by C. What is B star? What is B? B is here. B is perpendicular to both C and A. So the situation is like cubic. So beta star, B star is just 1 by B. Right? So now you can imagine, if I have to do it for triclinic, what will happen? The angles are alpha, beta and gamma. So each of these terms will have at least two sine terms. Sine alpha, sine beta, sine gamma, sine alpha, sine gamma. And also two among A and C and all that. So I would like you to go through the textbook and see the formula. You will get a better idea. I don't want to derive those because we have to do something else in the class. So this is how one can derive the reciprocal lattice constants for different unit cells. Is there any question at this point? We are dropping a perpendicular, cutting the perpendicular at a distance 1 by d of that and placing a point. That's what we are doing. Yeah.
We have no intercept along B.
Huh?
We have no intercept along B. We are only along A and C.
So what we are talking about B star is a plane which is like this, and from here I drop a perpendicular that anyway, since it is perpendicular here, because this axis is 90 degree here, 90 degree there. So when you drop a perpendicular here, it is already 90 degree. So it is simply 1 by B which comes here, right? That is the case with your cubic, tetragonal or orthorhombic system. Now I am going to draw only one axis instead of three. Suppose this is my A direction and I am starting from this origin O, and my edge length A is here. So OA is equal to A. So now, if OA is like this, I can have planes parallel to OA like that. All planes parallel to OA can be like this. All planes parallel to OA can be like that. All planes parallel to OA can be like this. Right? In any way, parallel planes are going to be like that. So what does it indicate? From this point, if I drop a perpendicular to this plane and I cut it at a 1 by d distance, it falls here. A plane which is here, I drop a perpendicular, distance is smaller, so 1 by d is larger, falls here, and so on. So the plane which are like this, all the reciprocal lattice points will fall in this line. If I have the plane like this, the reciprocal lattice points will fall in this line. So as a result, all these reciprocal lattice points that are going to be formed will form a plane where I will have points equidistant from the origin, like not equidistant, it will form a new lattice. It will form a three-dimensional periodicity. How? Let us see with one set of planes. Suppose this is A and this direction is suppose my B direction, and this is where it cuts 1. So this OB is the edge length B, suppose. So the plane which cuts this at that point has a distance d equal to 1 by b. Suppose that b is 10, then I chop it at a distance 1 by 10 and put this point. That is my reciprocal lattice point corresponding to d 0, 1, 0.